In this lecture notes, we'll continue with this example. In this example, we are given first a difference equation. This is a difference equation over here. And in the difference equation, when we are given that, it expresses a system. We can draw a system as a block diagram over here. And typically, we'll begin with a system that is relaxed. And the system is relaxed, meaning that all the memory is equals to 0 when we start. So if the input is 0 and all the memory is 0, then you realize that 0 multiplied by this multiplier, 0 xn minus 1 multiplied by this multiplier, yn minus 1 multiplied by this pi will give you 0. So a relaxed system means that when we start, the input is 0, the output will remain as 0. Now, in the past lecture, what we then did was that we have asked you to, from a difference equation, find the block diagram. Of course, in the quiz, we might do it the other way around. We give you a block diagram and we ask you to find a difference equation. Or in fact, from there, we can ask you to find everything else. Now, what we then do was that we have already figured out how to do the Z transform. The Z transform begin from the difference equation. We take the difference equation and we convert all this into YZ as well as XZ so that we can form something called H of Z. H of Z has a name. This name is called the transfer function. And once you have given the transfer function, then you would have a rational function of Z. And this Z, typically, if you get negative power of Z, because originally, now let me repeat this. So we have the difference equation, y of n equals to x of n plus x of n minus 1 plus 1/3 y of n minus 1. Remember that converting to Z transform is very easy. Y of n become y of z, x of n become x of z. And this guy is a bit special. Xn minus 1 becomes z of minus 1, x of z, and then the rest is trivial. Z minus 1 again because of this delayed signal, and this is y of z. Now we collect y of z together, so this is 1, and we move this part to the left-hand side, so it's minus 1/3 z minus 1. Right, remember that we are trying to group y of z together. That's why we get this equation. And x of z is also grouped together. We have 1 plus z minus 1. Now, we are always forming y of z over x of z because this is the output over the input. And this is the transfer function called h of z. So he has a name. His name is the transfer function. And you realize that this transfer function, when we start here, this is in the negative power of z. Okay, so many students are stuck here. What happened is that you realize that in the lecture notes, we have positive power of z. So all we are doing is multiplying the top and bottom by this because z over z is 1. So we are changing nothing. So we got z plus 1, z minus 1/3. And in fact, we are done with the transfer function. Given this, then we now can draw the pole zero diagram. So this is the real part of z, this is the imaginary part of z, and we always draw a circle, which is j. This is 1, this is minus 1, this is minus j. So where is 2? 2 is here. Where is minus 2? Minus 2 is here. All right, so we draw a circle first. So the circle is of radius 1, and then now we have to figure out these two values. When z is equals to minus 1, the numerator goes to 0. So where's minus 1? So we draw a circle here saying that z equals to minus 1 is a 0. What about here? When z equals to 1/3, the denominator becomes 0. So if the denominator becomes 0, h of z becomes infinity. So where is 1/3? Here. So this is 1/3, and then this is the pole of the hz. Now, when you draw the pole and 0, if we have one pole only, it's easy. You just draw a small circle here, And then now you're going to color, and then you say that this is the region of convergence. Now, why do we draw outside? Why do we find a pole and draw outside? Is because the system is causal, meaning that the impulse response exists on the right hand side. Stability will be asked. Since ROC, which is the hair, or this little guy, include the unit circle. Where's the unit circle? Which is that red line here. Okay, I better draw the unit circle for you. This guy, yeah, this guy that is now in purple is a unit circle. Since the ROC include the unit circle, therefore the system HZ is stable. We've done transfer function, we've done pole and zero, as well as stability. And the final two things we didn't do is Hn as well as Hej omega, which we are going to tackle. Now, let us tackle Hn first. So to get Hn, one of the answer is, of course, this box. Yeah, that means we start from here, we have Hz, and we perform inversely transform by partial fraction. That's one way. Yeah, so if you guys can figure out how to do this, this is one way. So you will arrive at the closed form solution, meaning that you have an equation showing you h of n. So this is one way. Very good. Another way, guys. So in fact, you already see that all the answers is here. By direct evaluation, we throw in xn is the impulse, meaning that we are going to draw it like this. 1, 0, 0, 0, and then all 0, and let this n equals to 0, and let this be xn. We throw this into the equation, either the difference equation or directly into this diagram, and then you can work it out by brute force.
Hi, Prof.
Yes.
Oh, so just want to ask, right? If you use brute force, right, what you get is like the discrete values for h of n, right?
Correct.
So you will get like n. What is the value at n equals 0, 1, 2,
Mm.
blah blah blah. So what, like, is it different from the closed form
Yes.
equation, and are you able to convert that into the closed form equation?
Okay, so let's try. Okay, so the gentleman asked, if I want a closed form solution, you cannot give me a sequence of number. So that's not closed form. But from a sequence of number, typically you can interpret what is the closed form solution. Okay, so let's try. So I pause the recording first. Right, okay, I'm going to draw the block diagram from the difference equation. Block diagram from the following. So to draw the block diagram is easy. We always start with x of n, and then we go out and we say this is y of n. So we have figured out this guy and this guy already. Now, the multiplier is 1 because he is multiplying by 1. What about this guy? He's again multiplying by 1. So, but he is being delayed by 1 sample. So this is x of n minus 1. Again, the multiplier is 1 because, yep. So, and then we are summing. So we sum. So the block diagram is very easy to draw if you follow it step by step. What about here? 1/3. So we get y of n. We now delay. And here is y of n minus 1. Now what about 1/3 is here 1/3. And then we sum. So this is the block diagram and we are done. So now we are saying, let us now figure out x of n. That's n. Okay, so we need x of n. We also need x of n minus 1. We need y of n minus 1. And we need y of n. Now, so what do? Remember, we start with a system is relaxed. So the word relax basically means all memory equals to 0. So what does all memory equals to 0? It means, who are the memory, guys? This is the memory. This is the memory. This is the memory. Okay, so we start with 0. All right, we start 0 here. So this guy is 0. We start with 0 here. So I'm going, and then xn. So if xn, let's say at time n equals to -1, this guy is 0. And therefore output is of course 0, because if this guy is 0, this guy is 0, this guy is 0, the output will be 0, because nothing is being multiplied and nothing is being added. Now, at time n equals to 0, something exciting happened. Why? What are we sending to x of n? To get an impulse response, we are now trying to find impulse response, right? Impulse response means h of n. Impulse response means x of n equals to delta n. What is delta n? What is delta n? I draw this for you.
1.
1, correct. But 1 at when?
When time equals to 0.
Correct. So that means at time n equals to 0, this guy is 1. The rest, okay, so this is 1. Now, what is this value, guys? What about xn minus 1? In fact, it came from here, right? Can you see? I draw the arrow for you. X of n will flow into x of n minus 1 when time increases. So this 0 goes to this 0. Can? What about y of n minus 1? Is this 0 flowing to this 0? So the output is 1. Correct. Because only, so now I better change. Our input is 1, and then 1 multiplied by 1, and then goes to the output. All right. What about time 1? So now our friend the 1 will flow here, right? Xn goes to here. What about here? Here will flow here, 1. This guy will be 0 now. And then now we have this table again, and all the values are present except yn. So yn is equals to 1 plus 1/3, 1/3. Now we draw the next table. 2. This guy flows to here, 0. Input is 0. This guy flows to here, 1 1/3. The output is 1 1/3 multiplied by, guys, 1/3. Now you can see the pattern already, guys. This is 1 1/3 multiplied by 1/3. The output is 1 1/3 multiplied by 1/3 multiplied by 1/3. Can you see now? So after a while, you realize, hey, there's a pattern, right? What's the pattern? The output is going to be 1 1/3 1/3. Keep on adding, right? 1/3 1/3. Oh, okay. And then if you can figure this out, you can already write the equation. I'll pause now and take questions. Okay. Resume recording. I'm going to use MATLAB to check. And then what I'm going to use is FV2. Why FV2 1 1 1 minus 1/3? It's because it came from this equation. MATLAB need you to express it in this equation for h of z. And then we look at the parameter. The parameter is z plus 1 over z minus 1/3. The parameter on the top is 1 and 1. The parameter on the bottom is 1 and minus 1/3. So once you have figured this out, which is on my top right hand side, you'll realize that all I need to do is to enter these two parameters. 1 1 on the top numerator, 1 minus 1/3 on the denominator. And the word FV2 stands for filter visualization tool. And now it allows me to plot the magnitude and whatever. So I'm going to show you the pole and zero plot. Remember, 1 0 is sitting at -1, and 1 pole is sitting at 1/3. So we got it correct. And now we want to figure out whether we got the impulse response correct or not. So what was my computation? Never mind. We press this little button and we'll get the impulse response. The first guy is 1. Okay, let's go and see our computation. The first guy is 1. And I draw for you this guy. When n equals to 0, 1. The second guy, 1 1/3. Let's see. Yes, third guy, 0.44. What is my answer? Is 4/3 times 1/3. 4/9. 4/9 is 0.44. So we got this correct also. What about the fourth one? We think it is times 1/3 again. Answer is 0.1481. 0.1481. So we figure out how to do it now because the next guy is again this value. So it is a geometric series, but the geometric series didn't start from when, guys? It start from here, the geometric series. Don't get confused. The geometric series didn't start from here. Or maybe from here to here. It didn't start from here, right? The geometric series didn't start from here coming down. It start from here, 1/3, then here, and then here. So this is the starting point of the geometric series. Okay, so if you write the equation of geometric series starting from n equals to 0, it's wrong. It's the geometric series start from n equals to 1. Now I take questions now. Right, so we figure out how to do h of n, and now we want to come to the final box. So this is the final box that we are interested in. H, E, J, omega, and what is it used for? So H, E, J, omega has also a name. His name is frequency response. He can be arrived from a few ways. By performing discrete time Fourier transform on H of n, if H of n is finite. If not, if it's infinite, you can't even try to do this. Can you see? Okay. So if it is infinite, immediately we are actually playing with H of z, substituting z equals to Ej omega, and we fire directly from here and we'll get to here. Okay, so in this example, in this particular example, you will realize that H of n is an infinite series. Yeah, it's partially a geometric series due to this guy. So we know that we cannot go from here to here because we can't even get Hn. You know, it will go to infinity. Since it goes to infinity, we can't even do this one. So maybe Andy's question is relevant only when H of n is a finite impulse response. We can go from here to here, get a finite impulse response, go from here to here, we get H Ej omega. For infinite impulse response, there's only one way. We go from difference equation to the transfer function, this guy, and then we substitute z equals to Ej omega to get this guy. So I'm now going to start to explain how and why. So I'll pause the recording first. All right, remember I promised that we are going to find h of Ej omega. And then this is called the transfer function. And then this guy is called the frequency response. And the question is, how do we go from this top to the bottom? Is nothing but substituting z equals to 1 Ej omega. So what do we do? All the z become 1 Ej omega plus 1 Ej omega minus 1/3. All the z is substituted with this guy. That's all. Okay, so you take a look at z, got z, which we like here to the z, here got z, change to here and here. Then now the question is, what is 1 Ej omega? Okay, now let's interpret 1, the absolute value. Omega is the angle because this is 1. This is the real part of z. This is the imaginary part of z. And then if I draw a circle, the unit circle again, any point on this unit circle is 1 Ej omega. So this guy is the whatever omega it is. For example, let's say this is how many? This is pi over 2. Maybe this is 0.75 pi. So this is 1 Ej 0.75 pi. What about this point, guys? 1 Ej, what? In polar notation, 1 Ej is pi. Or if you prefer 1 Ej minus pi, okay? Doesn't matter. All right, so you will realize that 1 ej omega is the unit circle. Where is it in the unit circle depends on omega. That's all. And omega can only be from 0 to 2 pi because 2 pi to 4 pi, same circle. Or 0 to minus 2 pi, same circle. Okay, so now we have already figured out this. So how to compute? Okay, we will always ask you this question. We want to compute h e j omega for omega equals to different values of omega. And the typical values is 0, 0.25 pi, 0.5 pi, 0.75 pi, and finally pi. So what are we drawing? We are asking you to draw 0, 0.25 pi, 0.5 pi, 0.75 pi, and pi. And then this is omega in radian per sample. And this guy is h of ej omega. First, I will ask you to draw the magnitude. And in the bottom figure, I'll ask you to draw the phase. Okay, can we compute the first guy together? So we have h of ej omega equals to 1 ej omega plus 1, 1 ej omega minus 1. Sorry, minus 1/3. Now let us let omega equals to 0. So we have 1 ej0 plus 1 divided by 1 ej0 minus 1/3. The answer is, somebody? 1 ej0 is easy, is 1 plus 1. This guy, 1 minus 1/3 is 2/3. Answer is 2 times 3 over 2 equals to 3. Did I get it correct? 3. Okay. Now let us use MATLAB. So remember, this is our system. So I always remember this system is correct because I look at the pole and 0. I look at the magnitude response. When you press this magnitude response, where is omega equals to 0? Omega 0 is here. This is 0 pi radian per sample. But look, hey, he is not 3. Why, guys? Why is he not 3? He's 9.5. Can somebody tell me? dB, yes, excellent. So we now convert dB to magnitude, and the answer is, wow, a nice 3. So now, I will plot 3 here. Now 3 is, actually the answer is 3 plus J0. So the phase is 0. So I will show you the magnitude and the phase plot together. So I press this button here. This button, the red line is the magnitude, and the red line is the phase. So magnitude and phase, 3 angle 0. Okay, so I got this right. And now I will color it here as well for my own recording. See? So 3 and 0. So now I go for 0.25 pi, and then so on and so forth, and then we are done. Cool. Okay, let's try one more. 0.25 pi. Okay? So 0.25 pi. H of, H of ej omega equals to 0.25 pi. And then how do I substitute? 1 ej 0.25 pi plus 1 divided by 1 ej 0.25 pi minus 1/3. Now, a lot of students cannot, oh, I'm talking to myself. Sorry. You get this? Yeah? So a lot of students cannot figure out how to do this. So what you must do is the top become a rectangle number, the bottom become a rectangle number, and then you can add, and then after that you must convert it to a polar number, and then a polar number, and then you can divide. Okay, that's why it's very, very painful. So let us now, you can see how I use MATLAB to do the top and the bottom. the top is 1 times exponential of 0.j times 0.25 times pi. So what is this number, guys? You think? Okay, so it will be 0.707 plus j 0.707 plus 1 divided by, then the bottom is also 0.707 plus j 0.707 minus 1/3. And then you figure out this is 1.707 plus j 0.707 divided by 0.707 minus 1/3. Oops. So it's this guy minus 1/3. Answer is 0.3738 plus j 0.707. So you see the top and bottom. Now you still have to, okay, you have to divide. So this is very, very painful, right? And unless you have MATLAB or a very nice calculator, I'll show you how my calculator does it. Huh? My calculator will do it this way, guys. I wouldn't even bother with all this, right? I'm just going to do it this way. 1 exponential, the top. So now I figure out the top, right? Divided by 1 times exponential of j times 0.25 times pi minus 1 divided by 3. And then I've got top and bottom and done. Can you see now? So I'm not even thinking when I'm doing this. So I know that y'all don't have MATLAB, but if you have a calculator that can do this, it'll save you a lot of pain. So let's see whether I get it right or not. So what do? I want to take the absolute value of all these, 2.310, and then the angle, EJ, minus 0.6918. So let me check. So I am evaluating at omega equals to 1/4 pi. So I'm interested in 1/4, 0.25 pi radian per sample. Okay, where is he? Let me look at the MATLAB. 0.25 pi is here. So 0.25 is here. Pi. Okay, 0.25 pi. Okay, it's about here as well as. Okay, I almost got it. I got 2.31, yes, for magnitude, minus 0.69 for phase. Okay, so I'm going to pause again and take questions. Question. If x of n is equals to 2 plus, let's say, cosine pi over 4n minus pi over 3, let's say this is 3, what is yn? And of course, we are assuming it's steady state. Huh? Okay, how to tackle this question, guys? So the answer is, we observe that x of n, 2 also can be expressed as 2 times what? Cosine 0n. Agree? What is cosine 0n? Cos of 0 is what?
1.
Yeah, so this is the same. Plus 3 cosine pi over 4n minus pi over 3. So you think that, hey, actually, the 2 is actually operating at omega equals to 0 radian per sample. That's one way to think. This guy is operating at pi over 4 radian per sample. So we have 2 signals going in. And because the system is linear, we can study the output independently. So we study output for x of n equals to 2 cosine 0n. Can? So output is yn is equals to, actually, y ej omega is equals to, what do you think I'm going to write, guys? Something x ej omega.
H E J omega.
Correct. What is H E J omega? We have already figured out, right? On top. Yeah. So the answer is here. 3 plus J0. Correct? Agree? Guys, can? Now, if you reach here, actually the interpretation is clear. Y of n is, I mean, you should express this as not 3 plus J0, but rather I would prefer you to express this as 3 EJ0 because it's magnitude of 3 and phase is modified by 0. So the output is, my input is 2. So it becomes 3 cosine 0n plus 0. So the second 0 comes from, so this is a green 0. Oops. This guy is the green 0. The 3 comes from 3. Oh, the original input is times 2. Right? So answer is 6 cosine 0n plus 0. So in fact, we don't like to write this. The answer is a constant 6. So the constant 2 goes in, and then our friend amplified by 3 times. So the output is 6. Clear so far? Anybody? I pause. Now we come to the harder part, the second part, which is this guy. Here we are sending 3 cosine pi over 4n minus pi over 3. So now we independently studying xn equals to 3 cosine pi over 4n minus pi over 3. And then let's find out E for omega equals to pi over 4. This guy, we have already figured out. The answer is, this is H of EJ omega equals to pi over 4. 2.31 EJ minus 0.69. Okay, so this is the frequency response at omega equals to pi over 4 radian per sample. What it means is he's telling you, if you send me a complex exponential at this frequency, I will multiply it by this amplitude and I will phase shift it by this phase. So my input is my complex exponential. Actually, there's 2 complex exponential. One is at positive pi over 4n. The other one is at minus pi over 4n. Why? Why am I saying that? Because remember, A cosine theta is equals to A E j theta. Can you remember, guys? What? Plus E minus j theta over 2. Do you all remember this Euler equation? Somebody typed in the chat for me, please. Or do you want me to explain this? Anybody? Can. Okay. So you realize that a cosine is made up of 2 complex exponential, one at positive frequency pi over 4, one at negative frequency pi over 4. So once you figure that out, actually, I mean, here we are only playing with complex exponential at pi over 4 positive frequency. But for cosine, it's very easy. The output is simply, my input is 3. My output y of n is equals to 3 times what, guys? 2.31. Yes, this guy. Then cosine pi over 4n minus pi over 3. This is the original equation, no change. But what else changed? Minus 0.69. Finish. So this is the output for this frequency. So overall, y of n is equals to 6 plus this guy. Because 6 comes from where? Come from omega equals to 0. This guy, second one, comes from where? This guy is for omega equals to pi over 4n. So in many exam questions, we always ask, we give you an input and we ask you what is the output in the steady state. Sometimes we just keep quiet about the steady state because that's all you can compute anyway. Okay, we are almost done. I will pause this and then now maybe you can see the big picture of what we have done today from this page and all the way to the final answer here. So with that, I'm going to pause the video again and I'll take questions